Welcome to Talk Tensors. If you've ever wondered how neural networks actually get their specific shapes and whether a machine could, fundamentally do that architectural design job better than a human engineer, this deep dive is absolutely for you.
Yeah, it is a really exciting one today.
It really is. Today, we are looking at the exact moment artificial intelligence started building artificial intelligence. We're unpacking a really classic seminal paper in machine learning called Neural Architecture Search with Reinforcement Learning by researchers at Google Brain, published back in 2016.
A huge milestone.
Exactly. Our mission today is to trace that incredible journey from human-crafted models to algorithmically discovered ones. We'll go deep into the ingenious methodology of using a controller to build child networks. Then we'll analyze the groundbreaking results on image and language benchmarks and trace the lasting influence this paper has had on the entire field.
What's fascinating here is that this paper completely shifted the paradigm. I mean, we went from humans painstakingly guessing network structures to algorithms systematically searching for the optimal architecture using reinforcement learning. It basically took us out of the dark ages of trial and error and proved that a mathematically grounded search process could just outdesign the best human engineers on the planet.
To really grasp how massive a shift that was, though, we have to jump in our time machine and head back to the machine learning landscape of 2016, because the field had just gone through a massive upheaval, right?
It really had. For decades before the deep learning boom, the central bottleneck in computer vision and machine learning was something called feature designing.
Which means what exactly in practice for people who might not have been coding back then?
Well, imagine you wanted a computer program to recognize a picture of a car. You couldn't just feed it raw pixels. Human engineers had to sit down and write explicit, highly complex mathematical rules to tell the computer how to find edges, how to detect corners, and how to measure textures.
Yeah.
You had hand-coded algorithms with names like SIFT, which stands for Scale Invariant Feature Transform.
Yes, yeah.
And HOG, which is histograms of oriented gradients.
SIFT and HOG, it honestly sounds like a medieval law firm or something.
It really does, but I mean, they were the gold standard. The problem, though, was that humans were forcing the computer to look at an image the way a human thinks they look at an image.
Yeah, that makes sense.
Yeah, so SIFT would look for high contrast points that don't change if you zoom in or rotate the picture. HOG would break the image into these tiny little grids and count the directions that the pixel color shifted. It was incredibly tedious, highly manual math.
And then the deep learning revolution just kicks the door down.
Completely.
You have AlexNet in 2012, followed by these massive networks like BGGNet and ResNet, and suddenly nobody is hand coding a corner detector ever again.
Because the community realized something profound. If you just give a deep neural network the raw, unprocessed pixels, and you give it enough labeled data, it will learn the absolute best features on its own.
It builds its own internal SIFT and HOG.
Exactly. The first layer will figure out edges. The next layer will combine those edges into shapes. The next layer combines shapes into car wheels or dog noses. It completely blew the manual methods out of the water.
But solving that problem just created a brand new one. We stopped handcrafting the features, but we started handcrafting the architectures. We traded one flavor of manual labor for another.
That's the perfect way to phrase it. The human bottleneck just moved further down the pipeline. Now, instead of asking, how do I mathematically define an edge, researchers were asking, well, how many convolutional layers should this network have?
Right.
What should the filter sizes be? Where do we put the pooling layers to shrink the image? Should we use skip connections to route data around certain layers? Designing these architectures essentially became a form of modern alchemy.
Alchemy is right. I remember talking to engineers from that era. You'd have PhDs at top-tier institutions basically functioning as highly paid config file editors.
It's so true.
They would literally tweak a few numbers in a text file, kick off a massive training run on the servers, go get a coffee, and come back 3 days later just to see if the accuracy went up by a fraction of a percent. It required immense expert intuition, but also just a staggering amount of blind luck and brute force time.
And naturally, when computer scientists see a manual brute force process, their first instinct is to automate it. But the problem was that the existing tools for hyperparameter optimization were severely limited.
You mean things like grid search or random search?
Yes, or even more mathematically sophisticated methods like basic Bayesian optimization.
Yeah.
They all suffered from a fatal flaw when applied to this specific problem. They could only search within a fixed length space.
Meaning they could only tune the knobs on a machine that was already built, rather than designing a new machine from scratch.
Precisely. If you had a network with exactly 5 layers, Bayesian optimization was fantastic at telling you that layer 3 should have 64 filters instead of 32.
Okay.
But it couldn't dynamically decide, you know what, this network actually needs a 6th layer, or I'm going to create a brand new branching path that splits off from layer 2 and merges back in at layer 4. They just couldn't generate variable length configurations. They couldn't invent structure.
Now, hold on. There were algorithms back then that could invent structure, right? I'm thinking of neuroevolution.
Yes, evolutionary algorithm.
Right, using genetic algorithms where you take a population of neural networks, mutate their structures randomly, see which ones survive, and breed them.
Modern neuroevolution algorithms did exist, and you're right, they were highly flexible. They could theoretically compose novel variable length models, but they had a massive practical issue, which was speed.
Because they relied on a random mutation.
Exactly. Evolutionary algorithms rely heavily on those random mutations. At the scale required for modern deep learning, like processing millions of high-resolution images, neuroevolution was painfully, impractically slow. It required too many complex heuristics to keep the mutations from completely breaking the models.
Okay, let's unpack this, because this brings us to the massive aha moment of this 2016 paper. The authors looked at this chaotic manual alchemy and made a remarkably elegant observation. They realized that the structure and connectivity of any neural network can be specified by a variable length string of text.
It is a brilliant conceptual leap.
It seems so obvious in hindsight. A network architecture is really just a list of sequential instructions. Add a convolutional layer with a 3x3 filter.
Right.
Next token, add array LU activation. Next token, add a pooling layer. If the entire physical architecture of a network can be represented as just a sequence of text tokens, well, by 2016, we already had AI models that were exceptionally good at generating variable length sequences of tokens.
You're talking about sequence-to-sequence models, the kind used for natural language processing.
Exactly. If an AI can translate a variable length sentence from English to French by predicting one word at a time, why couldn't it translate a blank slate into a state-of-the-art neural network architecture by predicting one structural token at a time? If the blueprint is just a string, an AI can generate it.
That insight forms the entire foundation of neural architecture search, which the industry now abbreviates as NAS. The authors formalize this into a system with 2 main components. The first component is the controller.
And what is the controller mechanically?
This is a recurrent neural network, or RNN. Its sole purpose in life is to auto-regressively generate those architectural blueprints, token by token.
And the second component?
The second component is the child network. This is the actual mathematical neural network that gets built by compiling the blueprint the controller just printed out.
So it's the physical realization of the string.
Yes. Once the child network is built, it gets trained on a real data set, like thousands of pictures of cats and dogs, to see how well that specific architecture actually performs at learning.
So the controller is the architect sitting at a drafting table, drawing up the blueprints, and the child network is the building that actually gets constructed, lived in, and stress tested. Let's look at exactly how this controller draws those plans. Let's say we want it to build a standard convolutional neural network, a CNN, for image recognition.
The controller operates autoregressively, meaning it predicts one specific characteristic and then uses that prediction as context to guess the next one. For a single convolutional layer, the authors set it up so the controller has to predict a sequence of 5 specific hyperparameter tokens.
Walk us through that sequence.
First, the controller's RNN outputs a prediction for the filter height. Let's say it guesses 3. It feeds that 3 back into itself as context and then predicts the filter width. Maybe it guesses 3 again.
So we have a 3x3 filter.
Right. Then it predicts the stride height, which is how far the filter slides across the image vertically. Then the stride width. And finally, the 5th token is the number of filters for that layer.
So it spits out 5 tokens, and boom, it has completely defined the mathematical shape of layer 1.
Correct. And then it just loops. It repeats that exact same 5-step process to define layer 2 and then layer 3, continuing to generate tokens until it reaches a predefined maximum depth, at which point it stops. The blueprint is finished.
But here's the multi-million-dollar question. In a normal language translation model, we use supervised learning. We know what the correct French translation of an English sentence is. So if the AI guesses the wrong word, we can calculate the mathematical error, run standard backpropagation, and correct its internal weights. But with this controller, there is no correct answer.
Exactly. There is no master blueprint.
There is no hidden blueprint it's trying to match. How does it know if guessing a 3x3 filter was a stroke of genius or a terrible mistake?
That is the crux of the entire operation. The only way to evaluate the controller's string of tokens is to actually build the child network, subject it to a full training cycle on the training data, and then test it on a held-out validation set.
So it actually has to do the homework.
It has to do all the homework. The accuracy that the child network achieves on that validation set, say 88% accuracy, becomes the feedback signal for the controller. In the paper, they denote this validation accuracy as the reward signal, or R.
So the child network comes back from the testing phase and basically says, hey, boss, your blueprint got me 88%. But how does the controller actually update its internal brain based on that single number? Because you can't just run normal calculus on this. Accuracy is non-differentiable.
That's right.
You can't compute a mathematical derivative for the abstract concept of adding a layer.
You've hit on the exact reason why they couldn't use standard supervised learning. The landscape of architectural choices is completely discrete and non-differentiable. You cannot backpropagate an error signal through a discrete text token.
So what's the workaround?
To solve this, the authors turned to a completely different branch of machine learning, which is reinforcement learning. Specifically, they utilized a policy gradient method known as the reinforce rule.
I know reinforce is a classic algorithm originally formulated back in 1992, right? How does it actually work in this specific context?
In math terms, the objective of the controller is to maximize its expected reward. Let's imagine the controller is playing a highly complex slot machine. It doesn't know how the gears inside the machine work because that's our non-differentiable black box. It just pulls a specific sequence of levers.
And those levers represent its architectural token choices.
The goal is to maximize the average payout, which is the validation accuracy it gets over time.
So instead of calculating an exact mathematical slope to the perfect answer, it's adjusting the probabilities of its guesses based on the payout.
Exactly. The empirical approximation of the gradient in the reinforce algorithm looks at the log probability of the controller making the choices it made and multiplies that probability by the final reward R.
Let's ground that for a second. If the controller guesses a really weird sequence of layers, and the resulting child network surprisingly achieves a fantastic accuracy, a huge payout, the reward R is very high. What happens to the controller's brain?
The reinforce update rule takes that massive reward and uses it to positively weight the gradients for those specific decisions. It essentially sends a signal backward through the controller's RNN that says, whatever internal mathematical state led you to assign high probabilities to those specific tokens, do a lot more of that next time.
And conversely, if it designs a network that just completely fails to learn and gets terrible accuracy, the low reward means those token probabilities get suppressed.
Right. Over time, through thousands of iterations, the controller gradually shifts its internal probability distributions. It slowly learns to favor the exact sequences of tokens that consistently yield high validation accuracy. It is fundamentally a trial and error process, but a highly directed, mathematically optimized one.
It sounds so clean in theory, but there is a notorious problem with standard policy gradients like reinforce, isn't there? The variance.
Yes, the variance can be catastrophic.
Why is that?
Because you are sampling discrete actions, guessing tokens one by one, and only getting a single scalar number at the very end of a long, incredibly noisy process, like training a neural network from scratch. So the gradient estimates can bounce around wildly.
Just due to the random noise of training.
Exactly. One REN might get 80%, the next might get 82%, purely based on the random initialization of the child network's weights, not because the architecture itself was actually better. If you just update based on raw reward, the controller gets confused and the learning process completely destabilizes.
So how did the Google Brain team fix the variance?
They employed a crucial standard technique from reinforcement learning called a baseline function, which we'll call B. Instead of multiplying the controller's probabilities by the raw reward R, they multiply them by the reward minus the baseline, so R minus B.
Like a grading curve?
Exactly like a grading curve. In this specific implementation, they define the baseline B as an exponential moving average of the accuracies from the previously generated architectures.
Let me see if I follow the intuition here. If the controller generates a new architecture and the child network achieves an 85% accuracy, Is that a good result or a bad result?
In a vacuum, you don't know.
Right. But if we use the baseline, if the previous 50 architectures the controller generated were only averaging 80% accuracy, then our new 85% result is fantastic. It's way above the curve. The R minus B math results in a large positive number, and the gradient update strongly encourages the controller to keep making those new choices.
But consider the opposite scenario. What if the running average of the previous architectures was 90%?
Then our 85% result is actually a failure. Even though 85 sounds like a decent number, it's below the curve. The R minus B equation results in a negative number, so the algorithm actively punishes the controller for those choices.
Exactly. By subtracting the moving average, the algorithm only explicitly reinforces architectures that perform better than the recent historical average. This brilliantly stabilizes the training. It reduces the wild variance without introducing any bias into the gradient estimate, allowing the controller to reliably converge on better and better blueprints.
Here's where it gets really interesting, though. We've talked about the elegant theory, the math, the grading curve, but let's talk about the cold, hard, physical reality of actually doing this in 2016. Because compiling a blueprint is fast, but training a child network from scratch on a data set like CIFAR 10 takes hours.
Oh, absolutely. Sometimes days, depending on the depth.
Yeah.
The compute bottleneck is immense.
Right. If the controller has to guess an architecture, wait 6 hours for it to train, get the reward, update its weights, guess the next one, wait another 6 hours. Doing this sequentially would literally take lifetimes. You wouldn't get a result before the heat death of the universe.
To make neural architecture search viable, the authors had to scale up the raw compute to an astronomical degree. The sheer distributed engineering involved in this paper is just staggering.
Right.
They couldn't run this on a single machine. They had to build a massive asynchronous parameter server architecture.
How did they actually distribute it?
They set up a central parameter server, which they divided into S separate shards. These shards stored the master weights, essentially the actual brain of the controller RNN. Then they deployed K separate independent controller replicas across their compute cluster.
So you have multiple copies of the architect working at the exact same time?
Right. Each of these controller replicas would sample a batch of different child architectures based on those master weights, and those child architectures were then deployed to individual GPU workers to be trained completely in parallel.
Wow.
Once a worker finished training a child network, it would send the accuracy back to its controller replica. The replica would compute the reinforced gradients and then send those gradient updates back to the central parameter server.
Asynchronously, I assume?
Yes. The central server is just constantly absorbing gradient updates from all these different replicas and updating the master weights on the fly.
Let's put some real terrifying numbers to this. In their main experiment on the CIFAR 10 image dataset, they used 20 parameter server shards. They deployed 100 controller replicas. And each replica managed 8 child networks simultaneously. If you do the math, that means at any given moment, there were 800 entirely different neural networks being trained concurrently on 800 discrete GPUs.
The scale of parallelism is mind-blowing, especially for 2016. They were essentially brute forcing the exploration of the architectural search space using Google's massive server farms, but guiding that brute force with the surgical precision of policy gradients. Only a handful of organizations on Earth had the physical infrastructure to even attempt an experiment like this.
But throwing 800 GPUs at the problem wasn't enough on its own. They also realized that their initial search space, that sequence of 5 tokens per layer we talked about earlier, was too simple.
It was too constrained. The basic CNN search space only allowed sequential layers. Layer 1 feeds into Layer 2, which feeds into Layer 3, in a straight line.
Right, a very traditional feed-forward setup.
But the most powerful human-designed networks of that era, specifically architectures like ResNet and GoogleNet, derived their immense power from nonlinear topologies. They used skip connections.
Branching paths. A layer deep in the network might receive input not just from the layer immediately preceding it, but from a layer way back at the beginning of the network. It allows gradients to flow more easily during training. But here is the conceptual hurdle. A string of text is linear. How on earth does a linear sequence of tokens invent a complex, branching web of connections?
To solve this, they implemented what they called a set selection type attention mechanism. It's a really brilliant addition. When the controller is generating the blueprint for, say, layer N, it doesn't just predict the filter sizes and strides. It pauses and uses an attention mechanism to look backward at all the previous layers it has already generated.
It's literally looking back at its own work.
Exactly. For every single previous layer, the controller uses a sigmoid function to calculate a specific probability. That probability dictates a simple yes or no decision, which is, should this previous layer be connected as a direct input to the current layer n?
So if we are building layer 10, it looks at layer 1, calculates a probability, and maybe decides no. It looks at layer 2, no. It looks at layer 3, and decides yes. Let's wire the output of layer 3 directly into layer 10.
And the mathematics of this attention mechanism are deeply tied to the controller's internal state. The probability of connecting an old layer j to the current layer I is calculated using the hidden state of the controller when it generated layer j, combined with the current hidden state at layer I.
It's very context aware.
Extremely context aware. It runs those states through some learned weight matrices and a hyperbolic tangent function. But the beautiful part is that because this entire skip connection decision process is governed by probability distributions, it slots perfectly into the exact same reinforced policy gradient framework we already discussed.
So the AI gets rewarded not just for picking good filter sizes, but for routing the data efficiently through the branches. But wait, this introduces a massive, very messy practical problem. When human engineers design ResNets, we spend hours making sure the matrix math lines up perfectly. If you were going to sum two layers together, they mathematically must have the exact same dimension.
They have to match perfectly.
Right. So if this controller is just blindly using attention probabilities to wire layers together in a massive 800 GPU cluster, doesn't it ever just build a completely broken machine that instantly crashes the server when you try to run data through it?
All the time. The authors term these compilation failures. It's a critical engineering problem. If the generated blueprint contains invalid math, say trying to multiply a 16 by 16 matrix with a 32 by 32 matrix, the child network crashes before it even begins training.
And if it crashes, it returns zero accuracy.
Patch number 2. At the very end of the network construction, the system gathers up all the layer outputs that haven't been connected to anything else, concatenates them all together into one massive tensor, and sends that combined data straight to the final classification layer. No data gets left behind.
And the third problem, the matrix dimension mismatch. What if it tries to jam a small feature map and a large feature map together?
Patch number 3. If the system needs to concatenate layers that have different spatial sizes, it simply pads the smaller layers with zeros until they scale up to match the exact dimensions of the larger layers.
It's completely brute force plumbing. It's not elegant, but it works. It acts as a compiler that completely shields the controller from its own syntax errors. The AI is free to wildly explore bizarre, non-intuitive topologies, and the system just quietly spackles over the hole so the training doesn't crash.
And that freedom is what allowed it to find such incredible convolutional architectures. But the paper didn't stop at image recognition. After conquering the macrostructure of CNNs, they transitioned to an arguably even more complex, nuanced problem.
Natural language processing.
Specifically, they wanted to see if the controller could invent novel recurrent cells.
This is the second massive contribution of the paper. Up until this point, if you were doing sequence modeling or language translation, you were using an LSTM, the long short-term memory cell.
The LSTM was introduced by Sepp Hochreiter and Jürgen Schmidhuber way back in 1997. And for nearly 2 decades, it had been the undisputed king of recurrent neural networks. It was a true masterpiece of human engineering.
Why was the LSTM so hard to beat? What makes searching for a recurrent cell different from searching for a CNN?
It's a fundamentally different challenge of scale. A seed-and-end architecture is essentially a macrostructure. You're stacking large building blocks, convolutions, pooling layers on top of each other. A recurrent cell, however, is a microstructure. You are designing the specific granular algebraic operations that happen inside a single step of a network.
Right, because an RNN processes a sequence of words one at a time.
Exactly. At every single time step t, the cell needs to take the current input data. Let's call it X subscript t, which might be the current word in a sentence, and the previous hidden state from the last word, H subscript t minus 1. The cell applies a series of mathematical functions to those inputs to produce the new hidden state, which it passes to the next step.
And the LSTM did this with gates.
The LSTM solved a massive problem called the vanishing gradient by using a highly complex arrangement of mathematical gates, forget gates, input gates, output gates, to tightly control what information is kept and what is thrown away.
So to beat the LSTM, the AI couldn't just stack layers, it had to invent new math.
To allow the controller to build a new cell from scratch, the authors had to completely redesign the search space. They conceptualize the inner workings of a recurrent cell as a mathematical tree graph.
A tree graph of computations. Walk me through this. Let's say we have a tiny tree, just 2 starting points. How does the AI actually choose the math operations? Like, how does it decide to add 2 things together versus multiply them?
Instead of predicting layers, the controller now predicts the nodes of this computational tree. It visits each node sequentially. For every single node, it has to output 2 specific tokens. First, it picks a combination method.
Which dictates how to merge the inputs.
Right, it dictates how to merge the 2 inputs arriving at that node. It can explicitly choose to add them together, or it can choose element-wise multiplication. Second, it picks an activation function to apply to that merged result. It can choose from a menu that includes tan, sigmoid, ReLU, or the identity function, which just means pass the data through unchanged.
And crucially, because they were trying to invent something that could rival an LSTM, they needed the controller to manage long-term memory.
Yes, and LSTM's real power comes from its cell state, which acts like a long-term memory conveyor belt running straight through the entire sequence, independent of the short-term hidden state. The authors explicitly require the controller to predict how to connect these memory state variables into the temporary mathematical variables being generated inside the tree nodes.
Let's ground this. In the paper, they provide an example of what they call a base 2 tree. Let's trace the exact steps the AI takes to build this simple mathematical cell. We have 2 leaf nodes at the bottom, let's call them index 0 and index 1, and they merge into an internal node at the top, index 2.
The controller RNN kicks off. It looks at the first leaf node, index 0. It outputs the token add and then outputs the token tan. Physically, what this means is that the compiled child network will take the current input word and the previous hidden state, multiply them by some weight matrices, literally add the 2 vectors together, and then wrap that entire result in a hyperbolic tangent function. We'll call that intermediate result a 0.
Okay, that's node 0 done. Then the controller moves to the other leaf, index 1.
For index 1, it predicts element-wise multiplication and ReLU. So the child network takes those same inputs, multiplies them by different weight matrices, performs an element-wise multiplication between them, and applies a ReLU activation which zeroes out the negative numbers. That result is a 1.
Now we have 2 intermediate variables, a 0 and a 1. But what about that long-term memory conveyor belt we talked about?
At this point, the controller has to handle the memory injection. It predicts that the previous memory state should be added to our first result, a 0, and then pass through another ReLU. So we get a brand new variable. Let's call it a new 0.
It's literally inventing algebraic formulas for memory retention on the fly.
It truly is. Finally, the controller moves to the internal node at the top, index 2, to merge the 2 branches. It predicts element-wise multiplication and sigmoid. So the network takes a new 0 and multiplies it by a 1 and applies a sigmoid curve. This final, highly complex mathematical result becomes the new hidden state output of the cell.
And as a final step, it has to decide what goes on the conveyor belt for the next step, right?
Correct. It predicts which of these intermediate nodes should be saved as the new long-term memory state to be passed to the next time step. Now that was just a base 2 tree. In their actual large-scale experiments, they didn't use a base 2 tree, they used a base 8 tree.
A base 8 tree? How big is the search space for a base 8 tree with all those combination methods and activation functions?
It gives the controller an incredibly complex, expressive search space of roughly 60 quadrillion possible cell architectures.
60 quadrillion. So the controller is essentially exploring a space of 60 quadrillion different mathematical formulas for memory retention, searching for the single configuration that best minimizes language modeling error. It's staggering. And that brings us perfectly to the experimental results. They built this massive 800 GPU architecture. They unleashed the reinforced algorithm, and they set it loose on 2 of the most rigorously competitive benchmark datasets in the world, CCAR-10 for images and the PenTrueBank for language.
Let's start with the CFAR-10 image results because the progression of the AI's discoveries is illuminating.
Right. So in their very first set of experiments, they intentionally kept the training wheels on. They told the controller you can only use convolutions and skip connections. You are not allowed to use pooling layers or strides to shrink the image.
Even within that restricted space, the controller discovered a highly efficient 15-layer architecture that achieved a 5.50% error rate on the test set. But what is truly fascinating is what this 15-layer network actually looked like when they visualized the blueprint.
This is one of my favorite details in the paper. Human engineers love symmetry. We love neat, logical progressions. If a human is designing a network, you see 3x3 filters everywhere, maybe a 5x5 if we're feeling wild. We predictably double the channel depth after every pooling layer. It's aesthetically pleasing. But when the AI spat out its blueprint, it must have looked like a bizarre typo to the Google engineers.
It totally defied human logic.
Right.
The AI utilized many rectangular filters, combinations like 1 by 7 followed by 7 by 1. It also consistently preferred to place the largest, most computationally heavy filters at the very top layers of the network, which runs entirely counter to traditional human intuition, where we usually start large and shrink down.
It's like asking an architect to build a house, and they decide to make the front door 7 times taller than it is wide, and they put the heaviest concrete blocks on the roof. To a human, it looks wrong, but mathematically, it works perfectly.
It found a shortcut we couldn't see. The authors proved it was a highly specific local optimum. When they tried to manually fix the AI's design by tweaking the filter sizes to look more normal, or manually adding or removing some of its bizarre skip connections, the performance immediately dropped. The AI had found a fragile but highly performant mathematical harmony.
And then they took the training wheels off.
In their final CFAR 10 attempt, they allowed the controller to predict tooling layers, strides, and a much wider variety of filter sizes. The result was a massive, sprawling 39-layer architecture, and this model achieved a staggering 3.65% test error rate.
Put that number in context for us. How good is 3.65% in 2016?
It rivaled the absolute best human-invented model in existence at the time. The reigning champion was a highly celebrated, meticulously crafted architecture called DenseNet, which sat at a 3.74% error rate. The AI design network not only beat the human state-of-the-art in raw accuracy, but it was also 1.05 times faster in terms of computational execution speed. It was a total undeniable victory for automated design.
So they conquered vision. But then we get to the Penn Tree Bank dataset, the PTB, for language modeling, where they deployed that massive base 8 tree search to find a new recurrent cell. Did they actually beat the LSTM?
They did. The results in NLP were arguably even more impressive. The controller discovered a novel recurrent cell that achieved a test set perplexity of 62.4.
Okay, for anyone listening who isn't deeply embedded in natural language processing, let's explain perplexity. What does a score of 62.4 mean?
Perplexity is essentially a measurement of how surprised or confused a language model is when it tries to predict the next word in a sequence. If the model is highly confident and correct, its perplexity is low. If it's guessing blindly, its perplexity is high. In language modeling, a lower score is always better. The previous absolute state-of-the-art human-designed model on the PTB dataset was sitting at a perplexity of roughly 66.0.
So the AI dropped it by 3.6 perplexity points. Is that a big deal?
A drop of 3.6 points at the very bleeding edge of a benchmark like the Penn Tree Bank is an enormous, highly statistically significant leap. Improving upon the highly optimized LSTM architecture was notoriously difficult. Brilliant researchers had spent nearly 2 decades trying to find a fundamentally better cell without much widespread generalizable success.
And it wasn't just more accurate?
No, it was significantly faster. The previous state-of-the-art model achieved its 66.0 perplexity by relying on a complex hack. It actually had to run its LSTM cell 10 times per time step just to squeeze out that performance. The AI-discovered NAS cell achieved its superior 62.4 score with standard single-pass execution, making it more than twice as fast as the previous best network.
But the real test of a discovered architecture, especially one pulled from a massive 60 quadrillion option search space, is whether it actually learned something fundamental about language or if it just aggressively overfit to the exact quirks of the PTB dataset. You have to test how well it generalizes to an entirely new problem.
Right. Generalizability is the holy grail. So the authors ran a massive transfer learning experiment. They took this exact new recurrent cell, which was discovered purely by training on word-level language modeling in English, and they applied it to a completely different task, character-level language modeling.
Predicting words versus predicting individual letters.
Exactly. And the NAND cell achieved a new state-of-the-art perplexity of 1.214 on the character task, beating out highly specialized human models that had been handcrafted specifically for characters. But the real mic drop moment of the paper involves Google's internal production systems.
Yes, the GNMT integration. This is the detail that completely blew my mind.
GNMT stands for the Google Neural Machine Translation Framework. This was Google's massive production-grade translation system. It had been meticulously hand-tuned by an army of world-class engineers over years, and it was deeply optimized to run on standard LSTM cells. It was an incredibly complex, delicate system.
And what did the authors do?
The authors took their newly invented AI-discovered NAS cell, and they quite literally just dropped it directly into the massive GNMT framework to translate English to German. They didn't retune the hyperparameters. They didn't adjust the learning rates. They did absolute zero tuning. They just swapped the old LSTM cells for the new NAND cells and hit run.
And the result?
It immediately improved the translation BLEU score by 0.5.
Now, a BLEU score is the standard metric for translation quality, comparing the machine's translation to a professional human translator. Why is a 0.5 jump such a massive deal in this context?
Because improving a mature production scale system like GNMT by even 0.1 BLEU usually requires months of dedicated engineering teams tweaking architectures. To get a 0.5 jump instantly as a completely untuned drop-in replacement is practically unheard of. It definitively proved that the AI hadn't just memorized the benchmark dataset. It had fundamentally discovered a mathematically superior way to gate and retain recurrent memory across the board.
But we have to play devil's advocate for a second. With 800 GPUs spinning for weeks, exploring millions of architectures, is it possible they just got incredibly lucky? What if a random number generator could have found that same cell if given the same amount of compute time?
The authors anticipated that exact critique, so they ran a crucial control experiment. They compared the reinforced policy gradient method against a pure random search.
Meaning the controller just picks tokens completely randomly with no learning or updating based on the reward.
Correct. And they proved conclusively that as the search progressed, the policy gradient method consistently found significantly better models and a much higher average of top-tier models than random guessing. The reinforced algorithm was undeniably learning the underlying structure of good design. They even proved the robustness of the system by injecting entirely new mathematical operations into the search space, things like the max function or the sine wave function, which you rarely see in neural networks. The controller was able to seamlessly navigate this expanded bizarre space and still find comparable, highly performant cells. It wasn't luck, it was optimized search.
The legacy of this 2016 paper is just hard to overstate. It single-handedly kicked off the modern era of neural architecture search. It proved that meta-learning, using neural networks to design or optimize other neural networks, wasn't just a fun theoretical concept to write papers about. It was a highly viable strategy that could consistently produce results superior to human intuition.
If we connect this to the bigger picture, following the publication of this paper, the field essentially exploded. Researchers globally realized that algorithmic design was the future. But they also immediately slammed into the massive limitation we discussed earlier, the staggering compute barrier.
Right. Only a handful of institutions like Google, Meta, or OpenAI can actually afford to run 800 GPUs concurrently for weeks on end. For an academic lab at a university, running a search like this would burn through their entire annual budget in a week. It was essentially an environmental hazard.
And that extreme cost led directly to the next wave of innovation. This paper catalyzed the development of much more efficient NAS techniques. Soon after, we saw the rise of ENAS, efficient neural architecture search, which forced all the child models to share a single set of weights, drastically cutting the training time from thousands of GPU hours down to less than a day.
And then came DARTS, right? Differentiable architecture search.
Yes, DARTS was a massive breakthrough. It relaxed the discrete, non-differentiable text token search space into a continuous mathematical space. This allowed architectures to be optimized using standard, highly efficient gradient descent rather than relying on the noisy, high-variance reinforcement learning process. DARTS made architecture search orders a magnitude faster and finally accessible to standard researchers with a single GPU. But none of that happens without the original Google Brain team planting the flag in 2016.
Still, we have to look at the blind spots of this original work. Beyond the massive environmental and hardware costs, there is a fundamental philosophical limitation to what this AI was actually doing. The search space itself was still rigidly defined by the human authors.
Yes. A human decided that the CNN should be defined by a specific sequence of 5 tokens. A human locked the RNN search to a base 8 tree and manually selected the exact menu of activation functions the AI was allowed to choose from.
The AI wasn't inventing entirely new paradigms of computing. It was just finding the absolute optimal path through a very large but ultimately finite maze that was constructed by a human. It's like giving a child a massive bucket of Lego bricks. They can build a spaceship or a castle that you never imagined, but they're still constrained by the shape of the bricks. The AI couldn't invent a new type of plastic.
That is a critical distinction. The algorithm was fundamentally bounded by the imagination of its creators. It optimized within the box. It did not step outside of it. However, acknowledging those boundaries provides the perfect jumping-off point to look toward the future and ask what happens when we start removing them.
Which brings us to my absolute favorite part of the deep dive, the novel notions segment. Now, a quick disclaimer for you listening. This segment explores outlandish but mathematically plausible new research ideas inspired by the paper's legacy. It is strictly for entertainment purposes only and does not represent actual current scientific experiments. All right, let's get weird. Idea number 1. I call this biological neural architecture search, or BioNES.
This is a fascinating extrapolation. What happens if we take this framework and step completely outside the digital silicon realm?
Exactly. The original paper applied a reinforced controller to lines of code. It outputted digital tokens that compiled into matrix math. What if, instead, we applied that exact same recurrent controller to a robotic bioprinter?
A physical machine printing living tissue.
Yes. Imagine a system where the controller isn't printing abstract mathematical operations like add or element-wise multiplication or digital activations like ReLU. Instead, the autoregressive tokens it generates represent physical parameters for printing actual living neurons onto a microelectrode array in a lab.
So the tokens would dictate the physical environment.
Right. The sequence dictates the chemical gradients applied to the petri dish, the precise physical microscopic distances between the lab-grown synapses, and the specific flow rates of nutrient solutions to different zones of the culture. The blueprint isn't math, it's a structural schematic for living tissue.
That completely redefines the reward signal, the R we talked about earlier.
Yeah.
In the digital paper, the reward was validation accuracy on a data set of images or text. In this BioNAS scenario, the validation metric, the reward fed back to the policy gradient algorithm, would have to be a physical measurement.
How would you measure it?
You would electrically stimulate the biological neural network through the array. The reward would be the physical organic culture's electrical efficiency. You'd measure its ability to sustain a stable, complex signaling loop without the cells degrading, seizing, or dying off over time. You use that physical electrical data to update the digital controller. The controller learns which spatial arrangements of real biological neurons result in the most robust computational wetware.
The implication here is wild to think about. Right now, humanity spends billions of dollars and megawatts of power trying to digitally simulate the human brain in silicon. What if we stop trying to simulate brains digitally and instead use neural architecture search to literally compile highly efficient, specialized organic compute clusters? You could have an AI design a biological processor specifically optimized for pattern recognition, print it out, keep it in a nutrient bath, and plug it into a machine to process data at a fraction of the energy cost of a GPU.
It forces us to view biology not as a sacred mystery to be unraveled, but simply as an alternative physical substrate to be optimized by meta-learning algorithms. But let's pivot.
A fully, infinitely recursive system.
Exactly. Imagine a controller RNN that doesn't generate a standard CNN or an LSTM cell. Instead, it generates a massive sequence of tokens that defines the architecture of a new type of controller. This Generation 2 controller then turns around and generates a Generation 3 child network to solve the actual data problem. When the child network evaluates its accuracy, that reward signal propagates backwards through time and structure.
So the reward updates the Generation 2 controller that built the child, but it also propagates further back to update the Generation 1 controller that built the builder.
Yes, and you let that loop run continuously.
The theoretical implications of that are profound and, frankly, a little terrifying. If you let an infinite recursive search run long enough with enough compute, the system might completely abandon human concepts of neural networks altogether.
It wouldn't need our Lego bricks anymore.
Exactly. It might stop using layers or convolutions or attention mechanisms entirely, because those are concepts invented by human brains to make the math comprehensible to other human brains. Because the recursive AI is free to invent the methodology of its own construction, it could iteratively discover a completely unrecognizable, highly nonlinear, non-differentiable alien mathematical structure. A structure that parses data infinitely faster and more efficiently than any human comprehensible math ever could. The AI fundamentally escapes the human-defined maze by inventing a higher dimensional space that we don't even have the vocabulary or the mathematical notation to describe.
It's mind-bending to consider where this is all heading.
So what does this all mean? It raises an incredibly important, almost existential question for everyone working in our field. Think about the timeline. If a relatively simple recurrent neural network in 2016, utilizing a reinforcement learning algorithm from 1992, could already invent better, faster, and more efficient architectures than the absolute best human engineers at Google Brain, what is our actual role in the future? Are human AI researchers ultimately just biological bootloaders?
Biological bootloaders is a powerful phrase.
Are we simply the temporary organic scaffolding required to write the first meta-learning algorithm? Are we destined to inevitably hand over the keys to the first truly automated recursive AI architects that will build the future of intelligence in ways we literally cannot comprehend? It is a deeply humbling thought.
It is the ultimate passing of the torch. The tool we built has finally learned how to build itself. Thank you all for joining us on this incredibly deep journey today on Talk Tensors. Keep questioning the blueprints of the algorithms running the world around you, because as we've learned today, those blueprints might not have been drawn by a human hand. We will see you next time.